Welcome to the 30th and the last lecture video for Physics 4C. In this lecture, we finally introduce the quark model and give an overview of the standard model of particle physics, wrapping up our coverage of optional topics of nuclear and particle physics. Having introduced Gell-Mann's eightfold way in the last lecture, we finally introduced the quark model, the underlying explanation for the pattern of mesons and baryons discovered up to that point. With the quark model introduced, we can now give examples of additional Feynman diagrams describing weak interactions. So we do that. And although we will mention strong interaction, because a strong interaction is not treated easily with the perturbative calculations, Feynman diagrams of strong interactions are not as illustrative. And finally, we wrap up with an overview of the standard model, along with some modern tweaks. The standard model is certainly not the last word in physics, but it is the current best explanation of the natural world, a theory of almost everything, as it were. Thank you so much for following our course content for the semester over the 30 lecture sets, adding up to more than 50 hours. I wish you best in your continued physics and science education into the upper division and beyond.
And I don't know if you can see it beneath me trying to erase it. When they actually detected a particle, it had a mass of 1672. So within 15 MeV, he was able to predict what the mass of this last previously undiscovered particle would be. So this is the Gell-Mann's way of kind of organizing all these zoo of particles that were discovered. And there's really an underlying theory. The underlying theory to all of these patterns. So this is, what you would call baryon decapulate or decupulate. So it's no longer a fold path, but that's just mysticism inspired name. It's not actual physical law. So the underlying theory is this is what Gell-Mann called it. This is around the time when people were becoming very inventive about names. He based on all this on a model he called Quark model. And I guess story behind the name is really, I don't want to say boring. I don't remember all the details. I only know it comes from some English poem. And the inspiration name, the crucial thing is that his idea was that these are made up of three more elementary particles. That neutron is made up of three particles called quark. Proton is made of another three particles called quark. And you can kind of see why why 3 would be the number. Because when you look at the spin here, spin 3 halves. So it must contain spin half particles in there somehow, right? How many spin half particles do you need, minimum, to make a spin 3 halves? You need minimum of 3 spin half particles, right? Now, can you get spin of 1 half with the 3 spin half particles? Right? Yeah, 2 of them add up to 0, add 1 more, you get spin 1 half. So assuming that these are both made up of same kinds of elementary particles that have spin 1 half, would fit both of these patterns. And with these more mundane, non-strange particles, we associate them with mundane, unstrange quarks. We give those quarks names up and down. So these are made up of up and down quarks. So U for up, D for down. And there is explanation behind why they are called up and down. It's a kind of allusion to idea of isospin that we never talked about, but it's related to spin. So the way I remember it is, proton is the isospin up particle, so it has more up quarks than down quarks. Proton has quark content of 2 up quarks and 1 down quark, because it's the isospin up from the old terminology. Neutron is the isospin down particle. So it has 1 up quark and 2 down quarks. So that isospin adds up to down. But that's the old terminology. So these d quarks, they are, I guess, let me see if I can remember it. So this delta plus plus, it should have 3 up quarks. And I guess I keep just adding down quarks to that. Wait, is that right? 3 up, I think that's right. And this will be 2 ups and a down quark, but somehow combined in a way that's different from proton. And spin 0, it should have a 1 up quark and 2 down quarks. And this should have 3 down quarks. All right. Now, this is how he, this is the, so to account for this strangeness, Gell-Mann introduced a new kind of quark. This is the new kind of quark that would be associated with this approximately conserved quantity. So strangeness of -1 is associated with what we call strange quark. That's really where the name comes from. So this is the strange quark, and I don't know if you can, well, you can kind of guess at some of the properties of these quarks. Let's start out with the up and down quarks. So suppose someone asked you, what are the charges of these up and down quarks? How would you answer it? What's the charge of down quark? Do you have anything here that you can look at to infer what the charge of down quark must be? Negative? Well, it's a negative sign, but I also want the magnitude. 1/3, yeah. You're looking at this delta minus, right? So if it's out of being made out of 3 down quarks, then this down quark must have charge of -1/3 E. It has fractional charge, so we've been calling E elementary charge, but well, it has 1/3 of E. All right, so how much quark should, so how much charge should the up quark have?
2/3.
Yeah, 2/3. You can do it, once you have inferred the charge of down quark, then you can do it with any of the particles. But charge that's consistent with overall charge is plus 2/3 E for the up quark. So, and once you have that, then all the other patterns fit. It explains why there's delta double plus, but no delta double minus. Because if you add 3 of the up quarks, then you get plus 2 E. But when you add 3 of the down quarks, you don't get plus 2 E. So with that in mind, now with these particles, we are trying to build them with only one strange quark, because it has only one strangeness, which kind of means we already know a part of quark content of these particles. So this must have one strange quark, one strange quark, and one strange quark. So the thing with +1 charge, how many of the other, so it must end up with 3 quarks. So the other 2 quarks, which of these do you think it should be? 2 ups, 1 up and 1 down, or 2 downs? Oh wait, would you know? I guess. Let's say this is the most positive one possible, right? So let's just say 2 ups. We want to make it as positive as possible. So 2 ups. Here it's slightly less positive. So let's say up, down, and strange. And here, I guess it's the most negative one. So 2 downs. So once you guess this, what would the charge of the strange quark be? Yeah, -1/3. So charge of the strange quark is the same electric charge as charge of the down quark. Okay? And once you have figured that much out, then the rest kind of fits in. With the C baryons, it has 2 strange quarks. So SS. So this must have 1 up quark. So it adds up to neutral charge. This has two strange quarks and one down quark, adds up to negative charge. Same thing here. I'm not repeating it here because you get the same thing. These are the excited states of these. But the thing that's new here is now this is the particle that must have three strange quarks, explaining its strangeness of -3. And explaining what else? I don't know. It's a charge of -1. And at this point, you would infer that this additional masses of 150 MeV, that must be how much heavier strange quark is compared to up and down quarks. So that's the underlying quark model. And when you first look at it, it is a nice model. It fits all the patterns we see. It explains everything. And once again, the most importantly, he predicted the existence of the omega baryon, and experimenters went out looking for it. And within 2 years, they found it in one of the cosmic ray tracks. Following the instructions of Gell-Mann, these are the kind of interactions that must be happening before this can be produced. So I think all of this must have happened around the 1950s, 60s. But after this is for 10, 20 years is the kind of dark period for the quark model. Because initially with this success, it looks so promising. So what would you do next if you really bought into this idea of quarks? That has this fractional charge of 1/3 or 2/3 E. What would you do next? You could find the mass of the quark, but what would you need to do before you can find the mass of the quark? You need to find the quark. You need to first isolate them, right? So people were now looking for free quarks. And free quarks would be something very easy to identify because it's the only particle we know that would have any kind of fractional charge. But what I will tell you is that free quark has never been found. So when you look at the literature of the time from the 60s, 70s, or even through 80s, you are going to see the phrase parton. And parton is associated with constituent parts of neutrons and protons because people did a deep scattering experiment with the neutrons and protons, got experimental data that indicated that the scattering result you get, kind of like with the Rutherford scattering, but high enough energy that you can actually go inside the proton. The scattering result you get is more consistent with the 3 scattering centers instead of just the 1. But when they were doing the experiment, they didn't give name quark to those particles they were seeing. They instead called it parton. And what it is indicating is a level of discomfort with the idea of quark because no one's been able to find one. And what's happening here? And so I guess I can tell you what hasn't changed. No one has still found free quark. Instead, we have what's called, you can call it by different names. Let me give you this phrase that you can search around and read up on your own. It's called quark confinement problem, or whatever, or color confinement. And you can think of this like a dark matter. Except I think it's better understood than dark matter. It's a name we have given to a phenomenon that we don't fully understand. But this idea of color confinement or quark confinement has been used to explain why we would never find free quark. And because as you try to separate quarks, there's so much more energy involved in it that you would produce a new pair of the quark-antiquark pair. And that actually represents a meson or something. That's associated with something called asymptotic freedom. You can read more about it on your own. But what I'm fessing up right now is that no one has seen free quark. But the reason people have come to believe in the idea of quark model is associated with something called November Revolution. And I guess in the interest of time, I'll just tell you what they discovered instead of going through the whole process of how they discovered it. So let me arrange my particles this way. So I kind of started out with leptons this way, electron, one, and neutrino, electron neutrino, one family of lepton, muon, and muon neutrino, another family of lepton. But with the mesons and baryons, I did this complicated listing of things. And in hindsight, this is a mistake because I'm trying to list elementary particles, and the evidence is that mesons and baryons are not elementary. They are made up of other particles. So let's just, for the moment, let's pretend that quarks are actually elementary. So, all right, let's list the quarks. So if you believe in the idea of quarks, then so there's an up quark that has, oh, I think I did it in the wrong order. That's fine. I have up quark and down quark. And each of these particles, there are properties you can associate with them, which is kind of how they are arranged. So they are all non-elementary fermions. Everything under this heading is a spin half particle. And once you start organizing them, then they kind of get organized by charge. So these all have charge of -1, and this the particle version does. These all have charge of 0, so it's more positive than these particles. I want to organize them the same way. Oh, so the way I should have organized them is actually this way. So the more negative particles here, so I would organize them this way. Down quark and up quark. So this is the first kinds of quark that we know about. Still spin half, fermion. And I guess the quarks that fall under this column here is going to have charge of -1/3 e. And quarks that fall under this category is going to have charge of +2/3 e. So with the discovery of strangeness, or with the strange particles, the additional thing you have introduced is the strange quark, which has charge of -1/3 e. So strange quark would fit here. Strange quark. Do you see anything missing here? Any obvious blank space that ought to be filled? Because otherwise it's aesthetically displeasing. This represents a new kind of family or generation of quark, right? So there must be something else that's paired with it. So this is the quark that we today give the name of charm quark. So you could call this the prediction of the quark model, that if quarks are a real thing, so we have this third quark, but you can just stop with the third quark because quarks come in pairs. So if we have strange quark, there must also be a charm quark. So the event I call November Revolution is the discovery of the bound charm quark state, discovery of the charm, anti-charm quark state that's today known as J/psi particle. So one of those particles that, one of the, I think, only particle that has two names because of simultaneous discovery. So two different groups, one called it J, the other called it psi resonance. And the discoveries were close enough that they both deserve equal credit. So, so that's what the particle is called now, J/psi. Who knows why it's not called psi/J? And it's a bound state of charm, anti-charm quark state. And that's and this validated the quark model enough for the particle physicists that even though we still haven't found free quarks, this is enough for people to say, we believe in this. You can't see quark, but we believe it's underneath everything because it explains enough. So we are, I think, into 1970s, not probably 1970s. I think this actually happened in the late 1960s. If you want to get the correct date, read through this note, because when I was writing up the note, I actually researched what I was writing, and I was sure to put down the correct date. But I'm not a good historian. I can't actually remember the actual date. So within this note, there's a place where I talk about the November Revolution. November Revolution. So mid-1970s, that's when those discoveries came about. And this is the plot that explains what they discovered. This is an energy plot of this is the energy plot of what they were measuring. They were measuring interaction cross-section, or how quickly does a new particle get produced. And there's a kind of underlying theory that says, the higher energy you go, the lower the interaction cross-section, unless you form something interesting, like a bound state, some kind of resonance. That's what these peaks are. And this peak here, very sharp, very narrow peak, that is associated with the J psi particle, is what they discovered. And it's a very sharp, very narrow peak because the charm quark, it's a new kind of quark. So apparently, in addition to strangeness, there's one more quantity that now needs to be conserved. Now we need to conserve charmness, or charm. So conservation of charm means now that, to get rid of that charm requires another charm violating process that takes longer. That means longer lifetime. So from energy time uncertainty principle, which I never really covered in this class, means these are become more longer-lived particles. So, so just to skip to the end, so at this point we have 2 generations of leptons and quarks, and at some point somebody discovers the 3rd generation. I don't know which one comes first. So I'm pretty sure this upsilon is the bound state of the bound state of the bottom and anti-bottom quark. So I'm trying to remember what got discovered first. This upsilon, a new meson state, or the tau lepton. But whichever one came first, somebody discovers new generation of particle. For our purposes, let's pretend that they found the upsilon first. So to explain this resonance here, new resonance, they come up with a new quark that now has a different quantity associated with it that has to be conserved. B, or the bottomness, or beauty. I don't know. I think bottom is the most common way. So the bottom quark continues to fit here. So now you have a bottom quark here. And it's like seeing a tip of the iceberg. That means there has to be more underneath. So having one quark in the 3rd generation means there must be the other quark. So they go looking for it, and top quark is, I think it was the last of the particles to be discovered because it's the heaviest of the quarks. And in fact, the top quark is so heavy, so unstable, that I don't think they've ever found the bound state of top and anti-top. That's never been found. I don't think it actually forms. And once you have 3rd generation of quark, then you would begin to wonder, hey, 3 generations, 2 generations, that doesn't really match. So that problem means there's a 3rd generation of leptons. And so for the purpose of this discussion, let's pretend that's what actually happened. Then someone goes looking for the 3rd generation of leptons, and they find it. And that lepton is called tau lepton. And we assume there's a neutrino associated with it. We call that tau neutrino. So these are the 12 elementary fermions that we know. 3 generations of leptons consisting of 6 elementary particles, and 3 generations of quarks consisting of 6 elementary quarks. So that's the introduction to quarks and leptons. So let me remind you of what Feynman-diagram represents. The Feynman-diagrams, they represent the interactions, and we actually talked about what's called QED, or quantum electrodynamic diagrams already. So but as a reminder, Feynman diagrams for QED. So I guess when someone says QED versus ENM, the distinction is QED is explicitly quantum mechanical. ENM, you wonder, is it classical electromagnetism or quantum mechanical electromagnetism? Is it relativistic electromagnetism? So QED, or quantum electrodynamics, is explicitly quantum mechanical description of electromagnetic phenomena that's relativistic. So in QED, what you are looking at is interaction of a charged particle with electromagnetic fields or photon. So QED elementary vertex is actually pretty simple. It's a charged particle comes in. It doesn't, it's actually charged particle comes in. It doesn't have to be fermion. It could be anything. Actually, how do I want to draw it? I guess the way I was gonna draw it was, I was gonna draw it like this. Charged particle comes in, goes out, and it changed the direction because it got hit by a photon. But really the thing is, you can take this, turn it in any direction. So this is describing how a charged particle is changing direction because it absorbs the photon, but you could draw this. You could draw a photon coming in that produces a particle and antiparticle. Particle goes out this way, and antiparticle goes out this way. And it's indicated as an antiparticle by arrow going backward in time. Now, sometimes people put bar here to indicate it's antiparticle. Some authors don't like this because it's like a double negative. Is it antiparticle or is it just antiparticle? But I don't know. For me, double negative means negative. It's an emphasized negative. Or you could do, so this is a pair production, kinda, or you can do pair annihilation. You could have a particle coming in, antiparticle coming in, and they annihilate to produce a photon. But I guess what I want to emphasize that all these 3 elementary diagrams are one and the same thing. They are not really different. It's imagine it like a Lego piece. You can take it, turn it around. In a very rudimentary sense. So I guess if you're being more sophisticated, it does represent a different dynamics. Now, I don't know if many of you remember, this elementary vertex actually, so for example, this idea of pair production, this actually does not happen. Right? There's no way to conserve energy and momentum at this energy. You could never have a single photon turning into electron and positron and have total energy and momentum be conserved in that interaction. This is how you can analyze it. Imagine a single gamma ray photon. You just go to the reference frame where the gamma ray photon is redshifted so that it's no longer gamma ray. Maybe it's a radio wave. So you can find the reference frame where your photon no longer has enough energy to split into electron and positron. And if that's possible at any frame, then that means, if something is impossible in any one reference frame, it's impossible in any other reference frame. Okay? So real pair production doesn't happen like this. Real pair production happens with the 2 photons. So this is an example of what these are. This is what we call elementary vertex. And it does, these do represent something in the actual calculation. These are first order perturbation calculations. It turns out all the processes you look at end up being second order perturbation calculation. So they always involve 2 vertexes or more. So the real version of this, where you have 2 charges going out, one let's say one electron and a positron. So you would have to start the process with 2 photons, so that there's a reference frame where 2 photons are colliding head-on, and however much energy they have is however much energy will go into electron and positron. So you have 1 photon coming in, another photon coming in. I'm pretty sure I drew this wrong. So okay, I cannot join this here because there's no elementary vertex that joins 2 photons together. So what I would need to do is, so photon here, here. Okay, so there's a vertex that joins this charge with this photon. And there's another vertex here that joins this photon with this charge here. Sorry, I haven't quite planned this out right. And in between these two, they are joined with a virtual particle, a virtual electron. And I guess for the sense of this direction, it really has to go in this direction. Okay? So this is let me redraw it so that it's a little bit prettier. So all the processes that you might imagine in electrodynamics can be represented with these Feynman diagrams. So this represents what we call pair production. And pair annihilation would be just take this diagram, flip it around horizontally, then you have electron and positron coming in, turning into 2 photons. So that's pair annihilation. I think we did the Compton scattering last time, right? Yes? Yeah. So there's Compton scattering. So that's the QED diagram, fairly simple. And it's fairly simple because you only have 1 elementary vertex. So any kind of, so I can give you an example. So when we are talking about mesons, it's still here, rarity. So neutral pion decays into 2 photons. So okay, we have to talk about the quark content of the pi meson. And what I should tell you now is that pi mesons are made up of 1 quark and an antiquark. And what can go into these rows for the pi meson are the up and down quarks. So for the neutral pi meson, it's going to be up and anti-up or down and anti-down. It's actually some linear combination of these. I'm not going to get into that. If you have different combination of up and down quarks, as in if you have up and, anti-down, then is this going to be positively charged or negatively charged? Positive, right? Plus 2/3, minus of minus 1/3, so plus 1/3. So this will end up with a Q of plus 1. Or if you have down quark and an anti-up quark, which is actually antiparticle version of this, this will lead to Q equals minus 1. So this is what pi plus is, and this is what pi minus is. Okay? So the purpose of our drawings for this neutral pion, let's say it's made up of up and anti-up quark. Then this decay, what it is it's a pair annihilation. So you have an up quark coming in, anti-up quark also coming in. So up, anti-up, and join them like this. Up quark emits a photon, real photon, turns it into virtual up quark. That doesn't have the same mass that real up quark would have. It also emits a photon again, and the virtual up quark, it doesn't turn into, the time sense is a little bit reversed. But this is the Feynman diagram that illustrates the decay process of neutral pion into 2 photons. Okay? So that's the basic principle. You can kind of play around with it, although I can't really assign homework assignments on this because my open math can't do it, so I don't know if I can actually give it to you on exam question.
How can we know the direction of the virtual particle? When we draw the diagram?
It's because the fermions have this, so these arrows have nothing to do with the direction of time.
Yeah, but how can we know we choose this way to draw the arrow?
Yeah, so this arrow only indicates is it particle or antiparticle. So this is particle coming in. This is antiparticle coming in.
Yeah,
So here, I'm drawing the arrows just to show that at this vertex, you have a particle line coming in and particle line going out. But it doesn't, it's a virtual particle. This particle doesn't actually exist. It's a calculational scheme. Yeah. Yeah, but this arrow, there's an unambiguous direction there. Now, if it's a photon, then there's no unambiguous direction for photon. Yeah. Yeah. So I guess whether you interpret this as a particle or antiparticle, that is ambiguous. Because if something is an antiparticle only if the direction of this arrow is going opposite to direction of time. Here, no direction of time, so you don't know, is it particle or antiparticle? I don't know and I don't care. Yeah. Yeah, so, but this is the basic idea of Feynman-diagram, that any reaction you have that involves electromagnetism, QED, quantum electrodynamics, it can be drawn with this very basic Lego block. Good? Yeah, I wish I could assign that as a homework, but I don't think there's a way for me to do that. I'll try that for next year, but whatever, I can't do it this year. So QED, it's simple. You have a simple one vertex diagram, so that's it. I guess you can practice on your own if you want. What I want to spend more time with, that's way more interesting, is the two other interactions, the weak interaction and the strong interaction, because that involves additional physics that we haven't actually discussed yet. And I think we have just enough time to tell you what's involved here. So let me redraw the interaction, the Feynman diagram for the weak interaction that I drew last Thursday. And when I drew it, I said this is not the actually correct diagram, but I drew it as kind of illustration of Fermi's theory of a weak decay. So the weak interaction, the early version looked like this. Let me do this as an example. A decay of a neutron into proton, electron, and neutrino. The way it was done was, well, you have a particle coming in, neutron, that decays into proton. So decays into proton, and in the process, it emits an electron, and it emits an electron antineutrino. Right? And this is what's called contact interaction. And the contact interaction has an issue. It's sort of like almost any contact interaction. It's like, you know, in physics 4a, we describe this kind of interaction as contact interaction. But as you get into smaller and smaller scale, you realize it's not really a contact interaction. This push here, this is an interaction mediated by a photon. Right? It's an electromagnetic interaction. So there's some virtual photon mediating, pushing of my hand on the table. So with the weak interaction, as you go into higher energy scale, that discrepancy becomes clearer. That when you continue to model this as contact interaction, the cross section for the interaction goes to infinity. You get another ultraviolet catastrophe, and you have to introduce a force mediator to avoid that. So I think I drew this much last time. The real version is that this emits a W boson, which decays into these two. I think W minus. I drew this last time, right? Yeah. So let me give you the elementary vertexes for the weak interaction. And in the process, I'm going to really need to introduce 3 more particles. Actually, 2 more, because 2 of them are antiparticle of each other. So let me draw the 3. Let me draw the 2, the elementary vertexes. There's technically 3, but once again, 1 of them is antiparticle version of the other. So I guess I'll continue to use this pen. So you know what? Actually, there are 3. Sorry, I do need to draw 3. So there's a version of a weak interaction that involves leptons. For example, electron and neutrino, or muon and muon neutrino. So that interaction would look like, let me draw it the way I drew this. So actually, let me turn this around. I don't kind of like how this looks. I think it's for comparison purposes, it's a lot easier if I have this version instead. So that it's kind of, particle, antiparticle turning into force mediator. That's an easier version to do it in parallel. So one kind of weak elementary vertex looks like, well, I have electron coming in, antineutrino coming in. So I have a lepton coming in, and I have an antilepton coming in. So not antilepton, the lepton, antineutrino. So neutrino of the version associated with the lepton, but the anti-version of it. They annihilate, and they form, I think usually people draw this with a zigzag. W boson. This is one of the boson's force mediator particles involved in the weak interaction. So let me start to add them. W boson. What are some properties of this W boson that you can infer just from the fact that all the conservation laws must hold here? What do you know about the lepton and the neutrino? Like some of their...
Those must have a charge.
Yeah, this must have a charge because lepton has a charge and neutrino doesn't have a charge. So the lepton, the particle version, has a negative charge. So that means this boson, W boson, must have a charge of minus. So the W boson, there's a one that has minus charge. Now, if there's one that has minus charge, then you just turn it into antiparticles, and there's a version that has positive charge. So there's plus and minus boson. So that's one of the elementary vertexes involving weak interaction. The second, at first sight, it wouldn't look different from this because I'm going to have W boson again. There's going to be another W boson. So what's different is not the force mediator, but what's different is the interacting particles. So it comes down back to the idea of approximate conservation of all these quantities. And the only interaction where the strangeness, charmness, and the bottom and top, where these have been discovered to be violated is weak interaction. So just like this interaction turns a lepton into neutrino, we should have interaction that turns, that turns a down quark into up quark, or strange quark into charm quark, or bottom quark into top quark. So that's the second set of vertexes. So let me call this one of the, no, I think I actually have to name them because it's not quark and antiquark. It's not the same version of the quark that's there. It's, for example, if this is down quark, then what's coming in here has to be anti-up quark. Can you check for yourself that the charge conservation holds at this vertex? Yes. Charge of minus 1/3 comes in. Charge of minus 2/3 comes in. Turns into charge of minus 1. Yeah. So that's the second vertex. It still involves the same W boson. And there's a third one that I have to tell you about. How do I explain this? I think somewhere in your textbook probably talks about this. It kind of is involved with direct detection of neutrino. Suppose you're looking for interaction where neutrino is involved. Let's see, is that? Let me just draw it. I think it's easier to do it this way. So there's a third kind of weak interaction, weak force carrier. It's what's called G boson, or the neutral G boson. It has no charge. It carries a weak charge, so it mediates weak interactions. And because it carries no charge, it cannot be involved in interactions like these two. If a lepton changes into neutrino, or one type of quark into another type, that must involve change of charge. So with this G boson, the only thing it can be involved in our interactions, for example, like this. Neutrino coming in and antineutrino coming in. So you can see a neutrino-neutrino scattering or neutrino-antineutrino scattering mediated by G boson. Well, it's not easy to see, but it can happen. So these are weak interaction vertexes. I guess I should, just as we did the QED, we should draw some examples of Feynman diagrams that illustrate the processes that we are used to seeing. And actually, this is where there's a lot of fun examples, so let me do a few. So I guess, where should I? Let me just list out all the examples that I want to do. So, so we started at the beta decay, right? About a week ago. So this is the elementary version of beta decay, neutron into proton plus electron and antineutrino. Let me do this, one. And we've been talking about pion. So the charged pion, let's say pi minus, decays into muon and muon neutrino, antineutrino. So I ought to be able to draw that as a Feynman diagram. Oh, and I have this. Let's see if I can draw that. Neutral K meson turning into, I guess I can two different versions. Two neutral pi meson or pi plus and pi minus. Let's do those first and then see if we want to do the more. Good. So the first one is the easy one. Neutron into proton, electron, and neutrino. You kind of pay attention to the quark content. Neutron has up, down, and down quark. Proton has up, and down quark. Yeah, so you kind of stare at it. What has changed? One of the down quark turned into up quark. So that's where you are going to draw this diagram. And whenever you have baryons involved, there may be spectator quarks, as in quarks that are not really involved in that interaction. You still draw them as a representation. So for that one here, you would have, all right, I have two spectator quarks, one up quark that's going to end up being up quark, and one down quark that's going to end up in the final process as a down quark. So the only quark that's interesting is the last down quark that's going to turn into an up quark. So I have a down quark coming in that at some point emits a W boson or virtual W boson. W minus, and then by emitting the W boson, it turns into up quark. So I have up, down, up. And what I'm not really drawing in these diagrams are hadronization or the interaction among the quarks that keeps this a bound state neutron and that keeps this a bound state proton. So there's a strong interaction involved in there that I'm kind of not drawing in my diagram, because that's the idea of spectator quarks. So this W boson turns into, I guess I'm using this one. Turn it around, so the W minus should turn into electron, or it could actually turn into muon, but let me talk about that in a bit. It should turn into electron and antineutrino. Right? Now, here's one of the reasons for drawing Feynman diagram. It lets you imagine what things would be like if they were different. For example, so I have all of this. So I have this W boson. Why couldn't it be, muon and muon antineutrino? Like, doesn't look like it has violated anything. So why couldn't this be muon instead of electron? Like, so that process never happens. So that must mean it's prohibited by one of these conservation laws. Which one?
Muon is heavier.
Muon is what?
It's heavier.
Heavier. So which of those conservation laws is it?
Energy.
Energy, right? Yeah, energy. Neutron doesn't have enough energy to produce proton and muon, but it does have enough energy to produce electron. All right, so yeah, so that doesn't happen. But while you are at it, I guess I haven't really mentioned the mass of the W bosons, right? So when you look it up, this is how heavy they are. W bosons, they finally found produced in the 80s or something. They are about 80 GeV, or about 80 times as heavy as a neutron. So what does that tell you about this? So, well, okay, what I will tell you is, so that is the mass of the real W boson. That's the W boson on the mass shell, has mass of 80 GeV. This is a virtual W boson. It can have whatever mass it needs to have to conserve energy and momentum here. So this virtual W boson has mass of like 1 MeV, and that's fine. Because virtual particles are not required to have the same mass that real particles do. Okay, so that's the first process here. Done. So let's do process 2, where a pion turns into muon and, so I thought of reusing the diagram, but I think it's easier to just redraw from scratch. So I need to first know the quark content of these. So pions, I think I've done this here. Okay, down and anti of quark. So I guess I can just draw it. So I have down quark coming in, somehow turning into anti of quark. And I think that's all. Oh, that's this exact diagram here. So this would turn into W boson. Once again, the virtual W boson, because pion doesn't have enough energy to produce the real W boson. And this virtual W boson decays into lepton and neutrino. So it decays into, I guess according to this, muon and muon antineutrino. Good? Oh, I guess it's actually a really simple process. Good. All right, now as you look at this diagram, I want you to imagine it again. Like, well, how would things change if this was electron and electron neutrino? Should that process be allowed? Based on what you know, there's no reason for that to be prohibited, right? So let me tell you this, and we are not going to get too much into it because we can't. Let's see, I can look at pion decay branching ratios. Okay, pi decay modes. So muon is the predominant decay mode. It does decay into electron and neutrino, but only about 1 out of 10 to the minus 4 times, 1 out of 10,000. It's a very puzzling fact until you are told, I guess, at least 2 more facts that I'm never going to test you on. The first is the idea of parity non-conservation. How many here are familiar with the word parity? That doesn't mean equality. It means something else. Parity, mirror symmetry. The idea that when you are looking at a mirror, and you move an arm, and it looks like it's another person in that mirror moving an arm. So physics out here looks the same as the physics inside the mirror. That idea is referred to as parity symmetry. And it's a very natural kind of symmetry that physicists have been assuming the whole time. And this is one of the really significant discovery in the modern physics, is that parity is not conserved. In fact, parity is maximally violated in the weak interaction. So once again, this is not something I can test you. I will tell you where you can read about it. And where you can read about it is in one of these optional readings. fall of parity. And you will, if you ever come across a particle physicist, you will hear this attitude, or any physicist actually, any experimental physicist. When you ask someone a question, they can answer with this. That's a matter of experiment. It's an experimental question. You ask them, you know, is electric force an inverse square law? And they will answer, that's an experimental question. And that's an attitude that's conditioned by fall of parity conservation, because that's what physicists were used to assuming is conserved. And when someone bothered to go out and check it, in the context of weak interaction, they found it's maximally violated. It's violated as much as it can be. And what you see here is kind of a hint at that parity is not conserved. One of the consequences of parity not being conserved is that neutrinos, they come in only one particular handedness. I think all the neutrinos are left-handed, meaning they, if they're traveling in some direction, then their spin is always, I think, anti-oriented with their direction of travel. So this neutrino always have to be produced with a particular spin state. Pion is a spin zero particle. So to conserve angular momentum, this has to come out with a particular spin state. And that's that's opposite of the spin that it naturally comes out. So in the interaction, it has to flip the spin of this particle. And so this is the second set of facts that you need to know. When these particles become relativistic, that spin flipping becomes much harder, something called the helicity. So the difference between electron and muon is that muon is heavier, so it's less relativistic than electron. So that spin flipping process becomes easier for muon. That's why it happens more frequently as a muon rather than electron. Once again, one of the curious things that you don't even notice until you think too much about it. So okay, so that's a step, process 2. Now K is, I guess, the interesting one, because this one, as you are looking at it right now, it doesn't even look necessarily like it should involve weak interaction. What would be a hint that it must involve weak interaction is once you start looking at the quark content of the K meson. So quark content of the neutral K meson would be a down quark. No, I don't know. I think it's, I might be messing this up. It's an anti-down quark and a strange quark. So that there, I know strange quark has charge of -1/3. So I need the anti-down to cancel out the charge, give me a neutral charge. And these final particles, they are all pions, meaning you can have only up and down quarks. So that means I have to get rid of a strange quark. So this is involving a quark changing operation. If it's electrodynamic, quark cannot change type. Only in the weak interaction, quark can change type from strange. So, I guess I should have noticed that. So this is the down and up quark version. So yeah. Let me first draw it and then I'll explain it. I think this is good. It's getting into features of this standard model that I've been meaning to get to. I think I'm getting to this as I'm drawing these Feynman diagrams. So we talked about non-conservation of parity. So what we are going to now talk about is, I didn't write it down. Under 3 generations, there's the idea of skewed generations that we need to talk about. So anyways, but let me first draw the Feynman diagram. That part is simple enough. I know what's coming in, what's going out. You just try to connect the dots. So the third diagram here, let me draw it this way. So I have an anti-down quark coming in. I don't think anything funny should happen to this. It can just be what it is. I'm not going to change the anti-down quark. So my anti-down quark will what it is from the beginning to the end. It's the strange quark that I need to do something with. So I have strange quark coming in. I'm going to need to change it to something that's not strange quark. So I have a vertex here, which involves emitting a W boson. And strange quark needs to turn into some other kind of quark. What other kind of quark can it turn into? Or let me ask the question slightly differently. So strange quark, it's coming in with a charge of -1/3 e. What kind of W boson can this be here? W plus or W minus? W minus, right? Carrying away this negative charge. Now, it's a little bit more than what it had. So you have to end up with a charge of plus 2/3 e, right? Which quark are we talking about? Up quark is a good candidate, right? Up quark has charge of 2/3 e. And in fact, up quark has to be one of these components here. So, I think I believe that. Let's say up quark. So this must be up quark. Yeah, let's leave it there for now, and then I will point out the thing that you worry about when you start thinking about these things too much. So this is what you have right now. You have down or anti-down quark and up quark, and this W boson is going to decay into a pair of up and, or I guess, down and anti-up quark. Now, if this decays like this, down and anti-up quark, then these particles would hadronize into neutral pions. Good? But it could also happen this way. So how would this happen? Well, for that to happen, I guess you just switch this around. So W minus boson, I mean, it decays into the same things. It said that down quark goes this way, anti-up quark goes this way. That's not right. In fact, that doesn't work at all. So because you can have two antiquarks. So this is the only way it can hadronize. If you want to get the possibility of producing positive and negative pions, actually this is what you need. Let me draw a separate alternate version. You have down quark here, and really the way it should go is this strange quark emits a W boson, and this strange quark, which turns into up quark, that hadronizes on its own. So that, this just hadronizes into pi plus, turns into pi plus meson. And this W minus boson, after it decays into down and anti-up quark, these two hadronize into pi minus. Okay? It's kind of a very subtle difference. It's a question of, essentially, it's a question of this. The two quarks that started out together as one K meson, do they end up together as one meson, producing another meson out of its own energy? Or does the initial meson essentially split into two? One quark forms part of one meson, the other quark forms part of a different meson, right? Now, let me ask you this question. Which of these two do you think is more likely to happen? Should they be equally likely to happen? I guess it's easier to start out with data. Or wait, you cannot look there because I'm not on the right page. So what I will tell you is this is actually more likely to happen than this. So let me just show it to you with the data that's available here somewhere. K meson, decay modes. Yeah, when you look at the two pion decay modes, the decay into two charged pions is more likely, about twice, is that the right number? Well, it's more likely than the two neutral pion decay modes. As in, this is more likely than this. And I can kind of give you a conceptual description why. This overhappening, the way this happens, requires additional constraint on it that's not here. So here, these two started out as two anti-aligned particles. Started out with a spin 0. And it ends up with a spin 0. And this ends up with a spin 0. So all of that is fine. You don't have to change anything. Here, so this has one spin. This has another spin. This produces two that has one spin, another spin. And those spins have to match up so that you end up with a spin 0 and end up with a spin 0. And in fact, if we had more time to spend with the isospin, that's actually what we do in one of the notes. With the isospin formalism, you can actually predict the ratio of the branching rate. Just, you don't know nothing about nuclear physics, but just on the idea that their spins have to match, or their isospin has to match, whichever. But those symmetrization requirements, you can kind of figure out that this is more likely to happen than this. And that's why in this data sheet, they are often expressed in these terms as in fraction, branching ratios, because that's an experimentally testable fact that can be used to determine spin of something. Okay, so that's the third one, I guess. And I should address one more thing. So it kind of half came up when we were about to talk about this vertex here. So okay, I have down quark. What's another version of down quark? What's another version of down quark? Strange quark, right? Okay, so this describes down quark turning into up quark. So shouldn't it also describe strange quark turning into charm quark? But here, we actually saw strange quark turning into up quark, not a charm quark. And what this is the idea of skewed generation. So I gave you these families of quarks as though they were like these families, these types, these flavors for all interactions. It turns out what counts as a charm quark, or rather what counts, I forget which is which. So you can think of it as two axes being slightly misoriented. So if you have an interaction involving, let's say, strange quark, in the weak interaction, so these two are supposed to couple together in, let's say, strong interaction. Then sort of the bases that count as these are skewed, so that there's some coupling in between generations from strange quark to up quark. It's a feature of, it's an experimentally measured parameter in standard model. Let's not go any more than that because I only have 3 minutes, and I still have one more interaction to cover, which is the strong interaction in the standard model. And I think that's about the right amount of time because it's a super complicated interaction. So I really don't want to give a lot of detailed description of it. I'll just give you an idea of the complication. So it's a sort of the idea of, I've referred to this as the hadronization here, the quarks forming bound states, right? And what I'm not really drawing here are the interaction between quarks. And the strong interaction, we say now it's mediated by a force boson called gluon, indicated with the letter G. And what can I tell you? So it's a gluon. As you might guess, its name comes from glue because it glues quarks together. I guess I should tell you there's 8 different types. There's 8 types of gluons. I'm not going to draw all 8. And some of you might have heard the phrase QCD, or quantum chromodynamics. Chromo as in color. This is where particle physicists get very fanciful. What they call color has nothing to do with literal color. Because like, what are you talking about? It's shorter wavelengths than visible, so there's no color involved here. What they are using is they are using the idea of color theory to express the symmetry that's involved in the strong interaction. I don't know how many of you color theory. What do you get when you combine red, green, and blue? What do you get when you combine these three?
Everything.
Not everything isn't quite right.
Gray or black?
Well, you're adding it additively. Not watercolors, but light. Yeah, you get white. So combining all these, oops, wrong color. You get white, meaning you get colorless state. So the charges that are involved in strong interaction, they come in three different types. So far with the electromagnetic interaction, there was really only one type, electric charge. It could be plus or minus, but that's like particle, antiparticle. With the strong interaction, there are three different kinds of charges. So there's red, there's anti-red, there's green, there's anti-green, there's blue, there's anti-blue. So like in a pion doesn't have any color associated with it. So this is what's meant by color confinement, that the particles we can observe has no color. So the way mesons are colorless is they always come in quark and antiquark. So the quark carries, let's say, red color. I'm simplifying this, by the way. Then the antiquark would carry the anti-red color, or blue, anti-blue, green, anti-green. Or actually, yeah. So that's how mesons are colorless. Carrying this analogy further, when you look at, for example, I don't know, I think I'm going to run out of time, which is, well, I think. So if you have, for example, neutron, up, down, down quark, then what we would say is, well, they have actually, each of these quarks carry different colors. So you have red quark, green quark, and blue quark. Once again, the names are simply a reminder for the symmetry that's involved underneath. So the symmetry of the quantities that are involved results in this combination, producing sort of a scalar state or state that has no color. So this produces the colorless state. And what I would tell you is that there is not much point in actually drawing strong interaction Feynman diagrams, because Feynman diagrams, the theories that they are supposed to represent are what's called perturbation theory, as in there's some underlying energy levels, and you're looking at what are the changes to the energy level. And the QCD, or quantum chromodynamics, it's you can do it perturbatively, look at small modifications to the interaction only at very high energy. So when you look at like a binding force of these three quarks, it's impossible. There's no good theory to, like, for example, predict mass of the neutron from the known masses of up and down quarks. It just doesn't work. So kind of interaction that you would represent are just a jumble of mass of quark gluon exchange from one to the other. Like there's no rhyme or pattern or anything. It's not, you know. If we drew something, it's going to be all very complicated. One thing I will tell you is each of these vertexes, the gluons, they are bicolored. They carry two colors. So if I have blue quark coming in, it would emit, for example, blue, and I don't know, let me just get an example of anti-red gluon. Then this quark going out here would now be red. Having gotten rid of red, it now has red color. So how many different kinds of combinations of gluons should there be? Just combinatorics, counting number of possibilities. You know, I think it can be red-red. So if it was, for example, blue, and anti-blue. Oops, wrong color. Just gonna use black. If it was blue and anti-blue, then this would simply remain being blue. Yeah, so you can repeat. So everyone here knows how to do combinatorics? First, you count the number of spots, 2 spots. And you should know what the number of independent possibilities. How many independent possibilities? 3. How many independent possibilities? 3. So how many different ways of combining these 2 independent possibilities? 3 times 3. You multiply them together, right? It's like with the independent probability. So there's technically 9 possible choices. It turns out one of the combinations like this is color neutral. This is kind of what I was referring to when I was saying this is kind of simplified. There's one combination of red, anti-red, blue, anti-blue, the green, anti-green, one kind of antisymmetric combination. That's the colorless state. So colorless gluon cannot mediate strong interaction. So you end up with 9 minus 1, 8 gluons. So I don't know how much of this I can test. So at a maximum, what I would expect you to know is that the particle mediating strong interaction in the standard model is called gluon. Let's leave it there. So I have this on the big projector because of the first thing I want you to cover today. So for the 1-hour lecture today, I'm just wrapping up particle physics, and I really want you to give you an overview of the standard model. And because I'm essentially trying to project this poster, it's bigger screen, the easier. And for the first overview, I will tell you that I had to specifically go find a version of this poster that's out of date. So the most up-to-date version kind of includes some complications that I would rather introduce under modern tweaks. So I want to first give you the overall basic features and overall structure first. And that's easier with the this older edition. I think this one was probably produced in 2012 or something. So this is the poster that I think that is exactly this poster. Yeah, so that is this poster. If you've looked at it and you've seen this. So this is the kind of overview of the standard model, what we know about particles. There are elementary fermions, elementary bosons. They also go by the name of force carriers. And so these are the particles that we know about. And these particles participate in these 4 fundamental interactions. Gravitational force, which we don't really deal with in particle physics. Weak electromagnetic force, which we know the best about. And the new things that we are talking about in the last couple of weeks, the weak and strong nuclear forces. And in the standard model, one of the big features of what makes the standard model is what's called electroweak unification. So here under bosons, it actually, even the older version puts it under unified electroweak bosons. And so photon is grouped together with the W boson and the Z boson. And I guess this work was done in the 1980s, I think. So I think I told some of you that there have been no new discoveries in physics for the last 30 years or 40 years. That's what I'm referring to. This big structural foundation of what we still call cutting edge particle physics was all settled in the 1980s. Possibly before I was born. So that's the standard model. And now there were some unverified features that's in the updated version that we'll talk about in about 20, 30 minutes. And I guess, so this is the good kind of good poster to look at, and we'll zoom into some different sections of it to just highlight the things that we've been talking about, the things we hopefully feel, begin to feel familiar with. And we'll spend a little more time actually looking at the properties of these things. So these are probably the particles that you are, well, okay, probable is not a good word. So in terms of your level of familiarity before this class, there aren't that many particles here that you would be familiar with already. So there's the electron that hopefully you feel familiar with. And you actually have to scroll down here for proton and neutron for familiar particles. But those are not elementary particles in our description of particle physics. So we have to start out with here, as unfamiliar as you are. Even quark, so I guess what you ought to feel more familiar with is the up and down quarks. If only nothing else, because these make up the particles that you are familiar with, protons and neutrons. So these are the 12 elementary fermions, not counting their antiparticles. So we talked about the concept of antiparticles. They are covered matter and antimatter. So for every particle type, there's a corresponding antiparticle type denoting a bar, blah, blah, blah. Particle and antiparticle have identical mass and spin, but opposite charges. Some electrically neutral bosons are their own antiparticles. Okay? That's a good short summary of what antiparticles are. So in most of these charts, antiparticles are not explicitly listed. So here we have 12 elementary fermion matter fermions. So for every one of these, you should imagine there's an antiparticle. There's a positron, there's antimuon, antitauon, and there's antineutrino for each one of those. So there are 6 elementary quarks that we know of, corresponding to 1 to 3 generations or families. And for each one of those, there are antiparticles. So there's 24 elementary fermions. Good. So some of the, I guess this is good time to kind of look at their properties in a little bit more detail. So we've been looking at their charge, or we know their charge already. We introduced the fractional charge of the quark and how that came to be deduced, even though we've never seen a quark. And you've been told some of the masses already. You know that electron is about half MeV. So this is in GeV per c squared. So this is the digit for MeV. So electron is about half MeV. Good. You know muon is about 100 MeV. Good. So one other feature I should point out is tau lepton, or tauon, is 1.7, 1.8, almost 2 GeV. It's almost twice as heavy as the proton. So lepton is more of a historical name now. Lepton, it used to mean that it's light, but today what defines a lepton isn't that it's light, because if that were the case, then tau, quote unquote, lepton couldn't be a lepton. The really defining feature of a lepton has to do with the interaction. So when you look at the interaction, so this is the second row is the particles experiencing these 4 types of interactions. When you look under strong interaction, only quarks and gluons participate in the strong interaction. Leptons do not participate in strong interaction. Lepton has no color charge, so does not participate in strong interaction. So that's what defines a lepton. So even though the tau lepton is actually heavier than heavier than the first 2 generations of quarks, or it's heavier than many of the baryons, it's still a lepton because it does not experience strong nuclear force. Okay. Quarks, so we spent a lot of time last time talking about the kind of guess at the strange quark, some time talking about the discovery of the charm quark, and I glossed over when bottom and the top quark were discovered and confirmed. I think I looked up the dates. Top quark was finally produced in 1995 or something. So, okay, I guess there are some, yeah, but people kind of knew top quark had to exist before that. Once they believed in the quark model, and once they found the upsilon meson, which is the bounded state of bottom quark, then it's a matter of, it's like, you know, if you believe in the periodic table of elements, then the undiscovered elements, you know, you believe they exist, even though people haven't actually found them yet. So, of these quarks, I will describe to you one odd feature. It's the masses of the quarks. So you've been told this fact or statement. You've been told that proton is made up of 2 up quarks and a down quark. And you've been told that neutron is made up of 1 up quark and 2 down quarks. Okay? What's the mass of proton approximately?
1 GeV.
Yeah, about 1 GeV, right? Per c squared if you're being, if you're being consistent with the units. And neutron is also about 1 GeV per c squared. Now, I invite you to look at the mass of the up and down quarks. Those are in units of GeV. Does this look like about 3 times up and down quarks? No, right? So I guess this is what so these numbers are hinting at a physics underneath that we didn't spend any time on. And that physics it's hinting at is that these up and down quarks inside the proton, they are relativistic. So most of the mass of the proton is not in the rest energy of the up and down quarks. It's in the total energy of up and down quarks. And really the more faithful model of the proton and neutron is that they are not just made up of these 3 quarks. These are sometimes called valence quarks or valence quark content. So this is the net quark content of proton. Really a better way to think about proton is it's made up of up and anti-up, down and anti-down, and these are kind of spontaneously produced in the kind of complicated strong interaction that these quarks are undergoing. This is part of particle physics that people have yet to figure out because So, but all these quark and antiquarks, they cancel each other out when you're adding up for net quark content. And what remains is this valence quark content. But really a more truthful representation of proton is that it's made up of a lot of indeterminate number of quarks and antiquarks. But when you add them all up, you have net of 2 up quarks and 1 down quark. Okay? And same for the neutron. So that's what those mass numbers are kind of hinting at. That if you're simply glancing at the chart, you could easily forget. These heavier quarks are actually easier to deal with in the quantum mechanical model of the nucleus, or the model of baryons and mesons, because they become heavy enough that you can use non-relativistic quantum mechanics, or not the quantum field theory. So like the bound states of bottom quark are more easily dealt with than bound states of up and down quark. So one more trivia. So when we say fermion, we do mean spin half particles. So spin 1 half, 3 halves, 5 halves. But as far as we know, all the elementary fermions have spin 1 half. We don't know of any elementary spin 3 half fermion. At least not in the standard model. I guess I don't know enough particle physics theory to know if there are any supersymmetric partners that's a spin 3 halves. But all the known elementary fermions are spin half. All right, so that's probably enough of the fermions. Okay, and we'll talk about the bosons. Those are the force mediators They are the force carriers, and they have integral spin 0, 1, 2. And I think actually we have an elementary particle for each one of those. So let's see, you guys know about photon. It's spin 1. We talked about W boson, right? It's also spin 1. And I guess for whatever reason on this table, at least here, they are listing all the particles, both the particle and antiparticle, because the charged W bosons are antiparticle of each other, and photon is its own antiparticle. Two photons can annihilate each other. And the neutral G boson is also its own antiparticle. Gluon, for whatever reason, they decided to list only one instead of the 8 different kinds that we were talking about last time. I don't know if they mentioned that, that there are supposed to be 8 different color charge. So gluon, they list only one, but if you go into particle physics theory, it is important how many different kinds of gluons there are, or how many different color charges there are. I said that we have spin 0, spin 1, and spin 2. So spin 0, that's one of the modern tweaks. They found the Higgs boson, and Higgs boson is a spin 0 particle. Spin 2, I think most people believe in this. Most people believe that there is some kind of quantum mechanical theory of gravity. We don't have one that works yet, but we believe it exists. And in the quantum mechanical theory of gravity, there ought to be a graviton. And that graviton, based on the symmetry that's associated with the general relativity, the only gravitational wave that can be produced is what's called quadrupole radiation, not dipole radiation. It's associated with the fact that there's no such thing as a negative massed particle. And the quadrupole radiation has to be associated with the spin 2 particle. So that's the elementary spin 2 particle that almost everyone believes they exist. So I'm going to pretend that it does exist. So those are the bosons. I guess I should point out one interesting thing that you see here that I kind of mentioned last time is just how heavy the weak force mediators are. Both the W and the Z boson, they are 80 GeV, 90 GeV, 90 times the mass of the proton. And that heavy mass is important in introducing one interesting question, and 2, explaining one interesting feature that I'm going to point to that's in this part of the poster in a little bit. One interesting question it raises is that when people start talking about the unified electroweak theory. So this is what unified theory means. It's kind of saying that when you are grouping these particles together, you are saying that they are brothers and sisters. They are comparable to each other. And you can especially see that here with up and down quarks. They are comparable to each other. In fact, you have interactions that turns up quark into down quark. So they are in some sense interchangeable, like a spin up electron in a magnetic field is interchangeable with a spin down electron. There are processes that will turn one into the other, right? So if you are starting to say that these are siblings, it's like looking at one person who's 7 feet tall, another person who's 4 foot tall, and they tell you they are brother and sister. It's like, how can you be? Don't you guys have the same genes? Why is one person so much taller than the other one? So here the particle physics question is, why are these so much heavier than the other? And the explanation for that is in what's called the Higgs mechanism. And that's where Higgs boson comes from. It's something called spontaneous symmetry breaking. So in the kind of, like a Pangea theory of particle physics, the very original picture, is that they are comparable to each other. They are all massless. But there's a mechanism that broke the symmetry and gave these particles mass. And the kind of mathematical procedure that does that says that there should be another kind of elementary excitation that should look like a particle, and that is the Higgs boson. Higgs boson, that's the theory that was proposed in the 1980s. That's the theory of unified electroweak interaction, and that's the kind of the last structural piece in the standard model, and that's the theory that was developed in the 1980s. And I will tell you that, Higgs boson was confirmed to exist in 2014. It would have been a bigger news if they never found the Higgs boson with the upgraded LHC. Like if they never found it, that would have been actually bigger news. Kind of more of a trickling news, but that would have been a bigger surprise to particle physicists than the fact that they found it. They've been expecting it for 30, 40 years. So of course they found it. So that's one interesting question raised by the heavy mass of the W and the Z boson. And that question is now answered in the affirmative in the discovery of the Higgs boson. I'll show you in the updated thing. And the other question that haven't quite been raised because we haven't talked about particle physics yet. It comes down to when you do actual, quantitative things with particle physics. So I guess I can actually use this diagram here. So I've been drawing Feynman diagrams. That's kind of a version of this, right? Two particles coming in, or a particle, antiparticle coming in, annihilating, producing a photon, that decaying into other things. You've seen those diagrams, right? And when you draw it as a Feynman diagram, with each of the vertexes, you associate a coupling constant or coupling strength. How strong is this interaction? And when it's an electromagnetic vertex, like with a photon, you associate a factor. When it's a weak vertex, like with the Z boson, or with the beta decay, with the W boson, then you associate a different factor with it. When it's a strong interaction with the gluons, then you associate a different factor here. And so this is the calculation that's actually done by particle physics graduate students with the help of the Feynman diagram. That's what the tool, the Feynman diagram, is for. And when you look at that coupling constant, the fundamental coupling constant, let's say electromagnetic coupling constant, you just set that at 1. It's actually 1/137, but let's just set it at 1 for now. Then the coupling constant for weak interaction, it's actually comparable to the electromagnetic interaction. It's not that very different. And in fact, it's this coupling constant that hints at the fact that electromagnetic interaction might be the same as the weak interaction, or that they are in the same family. But then the thing you have to explain is why in real life is the weak interaction so much weaker? And that's explained by the heavier mass of the W boson and the Z boson. So the heavier mass does two things. One, it makes the interaction short range. Because of the Yukawa type potential, there's an exponential decay that's associated with this mass. There will be one of the homework questions that kind of ties into that. And so that means at any appreciable length scale, that's what this is describing. And any appreciable length scale, like 10 to minus 18 meters, which is only like 1,000 times smaller than scale of nucleus. That times 30, it becomes a much weaker interaction. So this is the question, that these are similar, but these are not. And that question is answered by the heavy mass of the force carriers in the weak interaction. And strong interaction is, I guess I'm not really ready to get into it, so let's not. In lieu of going into strong interaction and color charge and all that stuff, let me just talk about the hadrons, or the zoo of particles that we mentioned before. They are in this chart of particle, in this chart of standard model also, pions. That was the original Yukawa's meson. So originally, we thought of nuclear force as being mediated by pion, and that's not entirely crazy model, but that's not the elementary interaction. The elementary interaction is mediated by gluons. So anyway, so pion, K meson. I guess we haven't talked about rho. I'm not quite sure what rho is supposed to be. I mentioned the eta. I don't remember mentioning rho. Rho is probably similar to eta. I don't know why it's in this list. One thing I guess it's different. It's a spin 1. So you can kind of look at it this way maybe. When you look at pion and rho, they are very similar, right? They are both. They both have the same quark content. So they have the same charge. Quark content determines what electric charge they can have. But they have two key differences. Rho is heavier, and it has a different spin. It's spin 1 instead of spin 0. So it's a sort of question of what gives. And this was the original evidence for what we now call color charge. It actually brings us back to something that you will be tested on exam 3, Pauli exclusion principle. Where does Pauli exclusion principle come from?
Exchange symmetry.
Exchange symmetry, right? So for example, when you look at, so I already said up and down are kind of similar to each other. So let's treat these two as indistinguishable particles for now. So pion is a particle made up of two indistinguishable particles. Especially if I'm dealing with the neutral pion, that's actually true. Here, you kind of imagine that it's true. Then when you exchange these two particles, the wave function you get has to be antisymmetric, which means they kind of have to be in a what's called a spin singlet configuration. Because, okay, so I can't test you on this because when we did this in the lab, I told you I won't test you on it, so I won't test you on this. But in the lab, what you saw was when you have a combination of spin up and spin down, two spin half particles that are combined in this way. So this is particle 1, 2, 1, 2. When they're combined in this way, this is what's known as triplet configuration. And the reason it's called a triplet is because this is a spin 1 state, as you saw in the lab. But I won't test you on this on the exam because I can't. Once it's a spin 1, then it has 3 different projections, 1, 0, minus 1. That's why it's called a triplet. This is a symmetric configuration. The antisymmetric configuration is given by this one that you guys guessed that in the lab. So the same state, instead of plus, it's minus, and then down and up. So this is known as the singlet configuration because it's a spin 0 combination. So 0 spin, there's no projection, there is really only one state. Okay? So that's why pi meson is in spin 0 state, and it all makes sense. Which means, what's up with this? What's up with the rho meson? I mean, everything is same. Are we suddenly saying that spin statistics theorem is invalid, that fermions can be in symmetric configuration instead of antisymmetric configuration? So whenever you come across this kind of crossroad in, I guess, fundamental science, you usually have 2 options. One is that whatever rule or law that you believed in before is wrong. Maybe there's something wrong with the spin statistics theorem, which means there's something wrong with the quantum field theory, and that's just invalid. That's one option. And the other option is there's something you miss. There's a particle, there's a parameter that you didn't know about before. And I will tell you, every time this decision has come so far, the correct answer has been there's something we missed. This was true with the neutrino, because the option there was, well, maybe energy conservation is wrong, but the option that we missed the particle turned out to be correct. And in this case, it turns out the correct choice was that we missed something, and that's the quantum number that's associated with the color charge. So with this additional quantum number, so overall even order symmetry, it's a multiplicative symmetry. So, so up to what you are seeing here, up to spin that you see here, this is in a symmetric configuration, but you can put the color charge in such a way that this is in a anti-symmetric configuration with respect to color charge. So you have an additional degree of freedom. Then everything, spin statistics theorem is fine, and this is still in an anti-symmetric overall configuration. So maybe that's why this is listed there. Anyway, so there's that meson. I guess we haven't talked about any of these, but these are some of the mesons dealing with the bottom and the charm quark. And there's a meson dealing with, I guess actually that's it. There are no known mesons that have the top quark in it. Top quark is so heavy and unstable that we don't know of any bound states involving top quark. All right, so those are the mesons. Once again, the top two are what you have seen and you may be tested on, but I'm not going to test you on the rest of them because there's just so many. And the focus on physics is never memorization. That's why you get only one index card. These are baryons. And there's a very nice distinction between baryons and mesons. And this is kind of why baryon number is conserved, meson number is not. There's no such thing as meson number conservation. And when you go back and look at the meson, you can kind of see why. It has a quark and antiquark. So when you look at the net number of quarks, mesons will always have net zero quark. So that's why meson number is not conserved. You can produce a pion out of vacuum. I mean, you still need a charge. So you can produce a neutral pion out of vacuum just with the photons. Baryons are made up of quarks, no antiquark. Or they are made up of net quark. So if it's anything like this, any antiquark that's there is paired up with a quark. So it's a net 3 quarks. So that's the proton that you know and are familiar with. There's the neutron. Now you can produce anti-baryons. They have antiquarks in it, 3 antiquarks, and everything is reversed except for the mass and I guess spin. You can't really reverse spin. This is magnitude. Let's see. Yeah, so every time you see a baryon, you can kind of imagine, with the right process, you can produce the antiparticle version of it. But to tell you the truth, antibaryons are hard to produce. I know they have produced the antiproton, and people have trapped antihydrogen. So, you produce antihydrogen by combining antiproton with the positron. And I don't know if they've actually produced antineutron. I thought as high up as antihelium was produced, but I'm not 100% sure. Anyways, so these are some of the baryons that you have seen. You have seen the lambda baryon, one strange quark, and we talked about the omega baryon. That's sort of the beginning of the quark model, because the quark model comes from the success of, I learned how to pronounce his name, Gell-Mann, success of Gell-Mann in predicting existence of this particle and how to produce it. That's really the beginning of the quark model. So, so these are the baryons. I don't know what else to say about them. Proton is the lightest baryon, that's why it's stable. I guess that's everything. Did I forget anything? So that's the standard model. So let me just do a quick count of things that are in the standard model, just so that we recap. So there are 4 fundamental interactions. Of those, the standard model really covers 3 fundamental interactions, but 2 of them are unified as an electroweak interaction. So there's really 2 different types of interactions in the standard model. All right. So I guess that's kind of the end of the elegance of the standard model. And then the rest is, so there's, as I said, there are 24 elementary fermions, including the particle and the antiparticle. there's 4 plus 8 elementary bosons. So there's 32 elementary, let's not count the antiparticles because that's not actually fair. So not counting the antiparticles, there's 12, and I don't know if gluon goes down from 8 to 4 if I don't count antiparticles. No, let's just, there's at least 12 fermions. And with each of those fermions, with each of those elementary particles, you need to associate 3 parameters: spin, charge, mass. So, okay, let's say for spin and charge, you just leave them be because they are kind of discrete quantities. Spin half and charge of 0 or minus 1, or 2/3 or minus 1/3. So, okay, so leave them alone. But with each of these particles, you have their masses. So the masses are not determined by theory, they are experimentally measured. So you have 12 elementary parameters. Yes?
How can you experimentally measure the mass of a particle that you haven't ever isolated, like the quark?
So they are measured in the deep elastic scattering experiments. And what I will tell you is there's an idea called asymptotic freedom. It turns out the interaction between 2 quarks works a lot like spring force. So if 2 quarks, they all work a lot like a spring force. It may not be actually spring force, but it sort of makes sense because anytime you have a stable equilibrium, you can always model it as harmonic oscillator potential. And so when the 2 quarks are very close to each other, the interaction, the strong interaction becomes weaker because the string is not as far stretched. So now in particle physics, closer distance means higher energy. So in higher energy, the strong interaction becomes smaller. So it becomes something that you can actually deal with more with the easier calculational methods. So there now you can begin to model what the interaction would look like for particular rest masses of these quarks. That's how the rest mass of the up and down quarks are determined. Because, that's how they're determined. And the quark, the interaction working like a spring force kind of explains why if you try to separate 2 quarks, then you will never actually be able to free up 2 separate quarks. Because at some point, it involves so much potential energy that there may be enough energy involved in this interaction to produce a new set of quark and antiquark. So as you try to separate out 2 quarks apart, what you end up doing is you produce new mesons out of that energy that's in the gluons. So as an answer to the question, how were those masses determined? In a scattering experiment. People jokingly say particle physics is like getting 2 Swiss watches, collide them together, look at the pieces that come out, and from the pieces that fall out, determine was in the Swiss watch. So, not quite that, but it's like that. And that's why particle accelerators are a big thing in particle physics experiment. High energy particle physics. Yeah? Oh, wait, I'm almost out of time. Wow. So let me then tell you, I think I've talked about some of the modern tweaks already. Let's see. Okay, I'll just show them to you. And there's one thing that I haven't recapped, but I mentioned it last time. These generations of quarks, this is a kind of an oversimplification because kind of distinction of something as up and down quark, it's according to the strong interaction. And the distinction of up and down quarks according to the weak interaction, they are not the same distinction. It's like having 2 different axes. They are rotated to each other. So I think the new poster might indicate that. So this is the newest version of that poster. It doesn't say, it doesn't say skewed generations. But really, what these are quark flavors according to the strong interaction. And quark flavors according to weak interaction are different. And that difference is expressed in an angular parameter. So those are additional parameters. And you will see some of the things have changed. These used to be called electron, muon, and tau neutrino. Now they don't. They call it lightest neutrino, middle neutrino, and heaviest neutrino. And I think it's kind of explained here. So neutrinos, I'll just read it out loud, are produced in the sun, blah, 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 many other processes. Any produced neutrino can be described as one of the three flavor states, weak flavor states, electron, muon, or tau, labeled by type of the charged lepton associated with its production. Each is a defined quantum mixture of three definite mass neutrinos. So a way of saying is this: these are the weak interaction eigenstates, but they are not the energy eigenstates of neutrino. These are the actual energy eigenstates of neutrino, for which currently a lot of mass ranges are shown on the table, and further exploration, blah, blah, blah. The backstory here is, for those of you who want to look it up on your own, look up something called solar neutrino problem. It's a problem that was only settled around the early 2000s. And the succinct description of that is, so these are produced in nuclear reactions. Our astrophysicists feel like they understand solar reaction well enough, so they estimate how many neutrinos from the sun we should detect. And when we build a detector and actually detect the neutrinos, with everything we know about them, we detect only a third as many neutrinos as we ought to detect. And the solution to that is something called neutrino oscillation. The neutrinos that are originally produced as electron neutrino on the journey from sun to us, actually more from the core of the sun to the surface of the sun, turns into different flavors of neutrino. The detectors we have, originally they were only built to detect electron neutrino. So that accounts for the missing 2/3. If those electron neutrinos turned into these two other types of neutrino. And a way to make that mechanism work is to say neutrinos actually have mass, and there's three different masses, and these are, so that's what, I guess I am out of time. So neutrino, that's one modern tweak. In fact, that's the latest change to the standard model. And this is kind of an easy tweak. This almost actually matches up the skewed generations I was describing in the quark sector. So it kind of makes sense that lepton sector also has skewed generations. So I don't think a lot of people are troubled by that. They still don't show the C of quark antiquark pairs, but that's fine. So this is produced after the Higgs boson was discovered. So it now has the measured mass, and it has the confirmed spin. It was, in theory, it has to be spin 0. Now we know it to be spin 0 from their measurements. I guess that's kind of it. That's the biggest thing. And I'm out of time to actually tell you why standard model cannot be the final theory. What's the best way to tell you in 1 minute? I think the best way to tell you in 1 minute is this phrase. You can search this on your own. So this is not something I will ever test you on. Search for physics beyond the standard model. It's an entire field of research. And the reason this is legitimate field of research is because every legitimate physicist thinks the standard model cannot be the final theory. And if you want to look at the listing of what's wrong with the standard model, you can look at, it is the first thing, problems with the standard model. And I will just tell you that this is the one that I thought most people found most convincing. And really this is the most unattractive thing about the standard model. That for a theory, fundamental theory of elementary interactions, it has like 2-3 dozen parameters. Well, okay, 1.5 dozen parameters. And it's when you have so many parameters, you can fit anything to match the observations. So a lot of people are uncomfortable with it. That's really why, at least that ought to be why there were people working on string theory, which has its own issues. It has more parameters than standard model. But so, I'll just leave that there.